Alright, in class today we tried to solve the problem where we have a shell that's flying through the air in a horizontal direction with some given velocity v0, and then it explodes in midair, and half of it, so a piece weighing 1/2 m, is now traveling downwards with that same v0, and then the other half, that goes off in some other direction. We decided it would have to be up and to the right in order to have momentum conserved. But now our goal here is to try and figure out, well, what is that velocity vector? Which way is that piece actually flying? So we're going to use, of course, momentum conservation, and that is written typically as P system. The change, in the momentum of the system is 0, because it's not interacting with its external or its surroundings significantly over this very small delta t. So because we do have that small delta t, we can say that f delta t, which is equal to the change in momentum of the system, is going to be 0. So we can just assume that. So our goal now is to try and find what the velocity is of the piece that flies off up and to the right with a mass of 1/2 m. So we start by writing that the initial momentum of the system better be equal to the final momentum of the system if nothing has changed along the way. So let's write these out as vectors. I'm going to assume a coordinate system where x is positive to the right and y is positive up, which means that my initial momentum of the system can be written as mv0, 0, 0. And then I can write the final momentum of my system in two pieces. So the first one is that, so this is then P initial here. So P final, the first part is that, we'll call it that chunk that goes straight downwards. So I can write that vector as 0 minus 1/2 m v0, because the velocity is given as v0, mass is 1/2 m, and it's going downwards. So in my coordinate system, that would be minus 1/2 m v0, and then 0. So that's the first piece. The second piece, I'm going to add this on, because all I'm going to do is the sum of the momenta. And in this case, I don't know either of the velocity components, x or y, as there's no z component. So I'm going to write these out as p2 final x and p2 final y. So these subscripts are going to get a little bit nasty. But the idea is that now we have an equation, or at least a set of equations we can solve. So we can take the x components from each one of these pieces, so I can take the mv0, 0, and p2 final x, and then the y components and do the exact same thing, and come up with, in essence, two equations that will give me what I need to know, p2fx and p2fy. What are the momenta of the two components of the momentum of that piece? So in the x direction, we have mv0 is equal to 0 plus p2fx, which simply means that the momentum of that piece in the x direction is equal to mv0. Well, that's not really helpful. That's not the answer really we're looking for. What we're actually looking for is what is the velocity of that piece. So the mass of that second piece was 1/2 m. So this would be m2, I guess you could call it, of that that second piece. And then we already know, or well, we can find out at least what the velocity is of that piece. So I'm going to write this as like v2 final x. So going from that equation we just had, we can solve for, in this case, the m's end up canceling out, and we get that the v2 final x, v2 final in the x direction, is simply twice that v0 that we started with. So that is the x component. So now if I take a look at the y component, you'll find that I have 0 is equal to minus 1/2 m v0 plus p2 final y, and that's what I have for the y component, which simply means that p2fy, I can solve this as that p2fy is equal to minus 1/2 mv0. Then, since I know I know m2 again, I know that that mass is 1/2 m, I can write this out, and then I have v2 final y. So I can solve for, again, this v2 final y, and just looking at this equation, we can already see that v2 final y is simply going to be equal to v0. So now I have that my final velocity vector for that part number 2 that we didn't know is 2 v0 in the x direction and v0 in the y direction. And lo and behold, that certainly does point up and to the right like this, so I could have an x component this way of 2 v0 and a y component this way of just v0, and then the magnitude of this, I guess, would be the square root of 5 times v0. And if you go through this, you can also notice that we actually end up gaining kinetic energy. We haven't talked about this kinetic energy yet, but we end up gaining kinetic energy in the process, and that kinetic energy, of course, comes from the fact that that shell exploded and it gave energy to the system. But it did not change the system's momentum. It did not interact with its surroundings, and so the change in momentum of the system has to be 0. And by the vector, I'm going to go ahead and assume